Okay, we're now recording, and I'm going to get a screenshot of our PowerPoint. Okay. We didn't get too far into Chapter 9 on Wednesday, but this is about where we started. So we want to start to think about this idea. Can you see it? Maybe not.
Yeah, we can see
I
it.
can see it.
Okay, very good. Thank you. Okay, so what we're doing here is we want to know something about the population, and we really don't know what a particular parameter might be. So we don't have an idea what the parameter is, but we're using sampling to start to understand that. And so there is only one value that represents the population parameter. And you could call it an average like mu, or you could call it a proportion like p, okay? So that is one value that represents the truth about the population. But when we start to sample, we have to play very conservative, okay, in terms of knowing that the sample mean, after we take many, many, many sample means, they are variable, okay? Now we know by sampling distributions that if we take the average of the sample means, we can actually close in on and determine the population mean. Okay, we all know that. So what we're doing right now is we're taking a sample and we're building an error that goes along with that sample. All right, and the sample, the actual mean, the population mean may be below that or above that sample mean. And that's what we're doing. We're building a sort of a interval. Okay, so we want a very accurate statistic, an unbiased statistic. And some of the things that go along with this, for example, we would like, for example, to have a distribution with a narrow distribution, so that the variance is very, very close to the true value. That then gives us precision about our confidence interval. So we want an unbiased situation centered on the true value, and we want also to have a very small variance, okay, or a very small standard deviation. Okay, so this is sort of unbiased, but the standard deviation is kind of large. This right here is also unbiased, and it has a very small standard deviation. And so you can imagine that this first one here on the left is sort of good, but the precision of the interval is quite large, okay? And so this here, the one on the right, is the best of the three because it's unbiased and a small standard deviation for more precision. All right. So we're thinking about proportions, okay? We go back and forth between proportions and means, and we can do that pretty well. And we might take a sample of these M&Ms, and we're interested in the proportion of blue candies, okay? How much confidence do you have in a point estimate? Okay. Okay. So what would we want for this interval? Okay, so a confidence interval for a population characteristic is an interval of plausible values for that characteristic, okay? All right. So understand that we're building this, this confidence interval for a population, okay? While we are using a statistic to do that, we really want to know what the population characteristic is. All right, so we want to, the primary goal is to estimate an unknown population characteristic. All right, so we can construct it with a degree of confidence. We actually have to put together some level of confidence before we even start with the building of the interval. Okay, so rate your confidence, okay? So I take this analogy, and I'll be brief about it. You know, you have your car, and you need some attention to your car, and you take it to a mechanic, okay? And you're saying, okay, I want to get my car, and I want it to be riding better. And so the mechanic looks at your car and says, yeah, I can do it, but I only have 75% confidence. Would you leave your car with the mechanic at 75%?
Probably
No. Okay, how about you had a confidence level of sort of 85? Would you leave your car with the mechanic? Maybe, depends. But if you had 95%, if the mechanic said, okay, I can fix your car and I have 95% confidence that it's going to run better, would you leave your car with the mechanic?
Yeah.
Yeah, you would.
Yeah.
Okay, and so 95% is sort of, you know, that's a good way of feeling good about what you're thinking. Okay, so this is a little cartoon here that goes through that sort of idea. So if we had a interval, okay, that was 10 years in between, will we have a precise sort of interval? What does this mean within 10 years? Well, that's a long time. How about 5 years? Okay, how about 1 year? Okay, and as you get lower and lower in terms of time, okay, you get more and more confident about what might happen within that interval. Okay, so that's what we're thinking about here in terms of confidence, the confidence level. Okay, what happened to the level of confidence with the interval becoming smaller? It became more precise. Okay, it became more accurate. Okay, so confidence level is sort of associated with the confidence interval, and we're thinking about the success rate of the method that goes into constructing a interval. Okay, so if this method generates an interval estimate over and over again, okay, in the long run, 95% of the resulting intervals will get us to where we want to be. That is understanding the population characteristics that we don't know. So our confidence is in the method of capturing the population mean, not necessarily in a particular interval. Some of the most common confidence levels are 90%, 95%, and 99%. And that is, these are called the confidence levels. Okay, common confidence levels. Okay, so let's recall the properties that go along with a sampling distribution of p hat. Okay, so the average of many p hats will be the same as the population p hat. I'm sorry, the population p. Okay, and here is the sigma that goes along with the sampling distribution and the variability. And remember, the sample size has to be less than 10% of the population. And we have conditions here that we must adhere to, and that is the sample size. The sample size is guided by the product between the sample size and p, and that has to be greater than 10. And the opposing side of the coin is also got to be greater than or equal to 10 to consider that the distribution of p hat is approximately normal. Okay, so we need pretty large sample sizes to deal with p. Okay, so we'll start with the confidence level of 95%. Okay, using a standard normal curve. The areas under the curve for 0.95 show that is the critical Z level below the mean and the critical Z level above the mean. Okay, so here is our standard normal curve with 0 at the center and standard deviations that go along with the scale on the x-axis. All right, so 9.95 is the area between these two limits, right? So this 0.95, these z-scores that go along with 0.95 are right here on the low end and right here on the high end. And you can sort of start to think about this as an interval that goes along with 95%. You could have it as a standard curve, but you could have it as a normal curve too. All right, so with that in mind, the tails have a area, okay, of 0.025 on both the low and the high. And so we want to start to think about what the z-score is for those two limits. And there is the z-score that goes along with those limits, negative 1.96 and positive 1.96. So we're going to be using the z-score to help us build a confidence interval. All right. So about 95% of the values within 1.96 standard deviations away from the mean on the low end and on the high end. Questions? Okay, so now what we're going to be using, this here, this term here is the sigma for the distribution of the proportion, okay? So 1.96 is the z-score times the standard error of the of P. All right. So within P hat, this error, we will capture the population proportion. That's what we're trying to do here. So we have P hat, which is the sample proportion. That's a statistic, okay? Something that we got from a sample. P hat minus the term here to P hat plus the same term, okay? All right, so let's start thinking about this a little bit. So here is the mean of the sampling distribution. You can call it the population proportion. You can call it the mu of the sample, the P hat. All right, and we're going to build a interval on the low end and another interval on the high end. So now we have sort of a look at what these are going to be. So you can imagine a more narrow distribution would give us lesser margin of error. All right, so here's a P hat. We just had an experiment and we got a proportion from that experiment, and we want to put on that P hat the interval that goes along with it. And that is the interval that is associated with this this confidence interval. Let's do it again. All right, so let's think about this. This is the term here is this distance right here. And actually it's equal to this distance too. This is the distance away from the center and it's staying the same. Okay, also understand that this interval captured the population proportion here. Okay, so we'll do another sample and we'll drop in that P hat. And again, it's somewhere inside of these boundaries right here. And this here is the same length as this right here. And again, this interval captures the mean or the proportion that goes along with the center. Okay, this third one though is now outside of the confidence interval. okay? So it's outside of the p hat, I mean, the proportion, the center of the distribution. It also does not capture p in its interval. So what are we saying? Well, sometimes we're going to get a sample that's outside of the limits of the confidence interval. Okay, so 95 times, 95% of the time, the p hat is going to be inside the interval. And 5% of the time, the interval will miss the center of the distribution. All right. So when n is large, a 95% confidence level is going to be this term right here. So this is a confidence interval. And all we need to know is p, all right, and p hat, and we can build at that confidence interval. So this picture right here looks at 100 different confidence intervals, okay, with the same interval on the end. And sometimes these intervals, most of the time, these intervals capture p, and sometimes they don't. 1, 2, 3, 4, 5, 6, 7 times it didn't. If we did this again, we probably would get different values, but over and over again, it will be 5% of the intervals will be outside of the and miss p, and 95% of it will capture p. Okay, so let's think about a more normal or general formula about the population confidence interval. Okay, so p hat has to be coming from a random sample. The sample size has to be large and fit in with these assumptions. Okay, and the sample is selected from a population of quite a large proportion without replacement. So this general formula for a confidence interval or population proportion is this equation right here. P hat plus or minus the critical value, which is a z-score, times the, actually this is the margin of error here, but this is the standard deviation of the proportion. So we have a point estimate. We have the standard error. Please understand that this term here has the standard error in it. Okay. So the standard error is the sort of it's equal to the standard deviation of the sampling distribution. And so we're going to call this the bound on the error estimation. Now that's a pretty tough phrase to to get out. So I'm going to call it the margin of error. So this here is the standard error right here. Here's the critical Z value, and the product between the standard error and the critical value is the margin of error. Okay, so let's run through this example. All right, so we have a situation where we have 1,031 adult Americans. We're thinking about the utility of getting a college education, and they were surveyed. 567 indicated that the college education is essential for success. Okay, so the P hat is 564 over 1,031, and the proportion there is 0.55. What is the 95% confidence interval for population proportion of adults in America believe that college education is essential for success? Okay, so we need to verify all the conditions. First thing is, does it satisfy the sample size is large enough? And of course, we have 567 here, 364 here, and that is greater than 10. Okay, we can feel comfortable that the sample size is smaller than the population size, that is adult Americans. Okay, and we can say that the sample was randomly selected and represents the population. So all the conditions are verified. So we're set to calculate the confidence interval. All right, so we're looking at 95% confidence. Okay, so that gives us the Z-score. Okay, that value here, 95%, is going to give us the critical Z-score, and then we have the standard error of the proportion. So here is the P hat. 1.96 is the Z-score that goes along with 95%. So we can take 0.55 times 0.45 over the standard, over the sample size. And here then, 0.521 to 0.579 is the interval. Okay. So what does this interval mean in terms of the context of the problem? Okay. We are 95% confident that the population proportion of adult Americans who believe that college education is essential for success, and that is between 52.1% at the low end and 57.9 on the high end. So here is our confidence interval given these conditions. Questions about that? Questions? Okay, well, I have to run to a 10:30 meeting. I'm sorry to cut the lecture short, but I'll pick it up again on Monday morning, 10 o'clock. Looking forward to it.
Thank you.
Thank you.
Thank you.
And a good weekend. Be safe.
You too.
Thank you. Okay, I just have a quick question. Are you going to assign any homework for the weekend for this chapter, or probably no?
Not yet, Taylor. I have a little bit of leeway between Monday and the day of the last test. Okay, you might
Okay.
see some homework assignments during that period of time. Okay,
Okay, thank you.
does that make sense?
Yeah.
Okay, thank you a lot. Have a good day.
Thank
You
you.
too.
Have a good day.